I just want to give you guys quickly the idea of a flux integral. Yeah, count 3 is fun because you get really neat words like flux integrals.
Do they use that in fire dancing? Flux torches.
Yeah.
Yeah, that's why I think too.
Okay, so here's the idea. I have some little net out in the world, right? Really, a prop would be nice. All I have is a dirty rag as a prop, so I'm not using it. But say you had some net.
There's clean rags over there.
I'm gonna go with my picture. And then you had some vector field flowing along, right? You guys all good with this? So I've got some membrane in the world and I'm flowing some fluid through it, right?
Yeah.
I might wonder, right? Like, what's the obvious question here?
How fast?
Yeah. How much stuff goes through the membrane? Have a seat. So how much stuff passes through? Does that seem like it makes sense?
Yeah.
Okay, so how can I figure that out?
Rate per unit area times the total area.
Yeah, really I'd like to do something like this. I'd like to take a little chunk of this area, right? And I might wonder, how much stuff goes through that? Yeah.
Do you mean like pokes through it?
So maybe let me pretend I have my vector flow is kind of this way, right? Here's my little bit of area, right? But my arrows, they point like this. So are they going through? Like, what if they pointed this way? What if my flow went this way? Would I be passing through the net at all?
I mean, kind of like light through a window, it gets reduced.
Yeah, one thing you could wonder is how much light is passing through a window, right?
Yeah.
And if the angle is straight on, right, then you're getting lots of light through the window. But if the angle's really oblique,
So
Right.
there's still gonna be dot products probably.
yeah, there's still a dot product. I mean, that dot product here really makes sense. We're just going to integrate, right? We're going to add up all the little squares, and what are we going to add up? Well, we're going to add up the vector field, right? Dotted with whatever a changing area might look like. You guys see that? Okay, so let me give you some alternate notation so you can actually spend a second calculating these. Because this notation, like the other one, right? I'm integrating over some surface, some flux dotted with whatever the heck d area means. Right, but much like the other one, this doesn't make any sense really, it's just the idea. So this is really me defining the idea of flux. We're going to define it that way. That's a flux integral. And when you go to execute this thing, the way you're going to execute it is you're going to do the integral over the surface of f dotted with a normal vector times the usual change in area. You guys see that? So again, this is like idea from last time. Execution.
It's like if your area is small enough, the line going through it is just a normal vector.
Yeah, you guys see that?
So
So that's, here's my area, right? If I've got my normal vector sticking out here, and my flux passing through, if I want to know how much stuff is flowing through that little square, it's about the dot product between the two times the area of the little square.
Is that,
And if,
is that normal vector, unit vector?
Yeah, so I have to figure some things out about that normal vector, but for right now, I just want to go with that idea that it's a normal vector.
So by that theory, the normal vector, if it was perpendicular to the sort of field going in, it would be 0.
Yeah, perfect, right? So if you had your normal vector for your area, right, and your flow were perpendicular to that, then of course nothing's passing through, so your integral is going to be 0.
So if you pointed a laser beam at a window and that the 2 lines were perpendicular, it'd be 0.
Yeah, exactly. If you put a laser beam along a piece of glass, right, none of the lasers going through the glass. You good, Fern?
Yeah, just like if the normal vector, like if it was the board, and it was pointing towards us,
Okay.
and the flow was pointing in towards the board,
Okay, so normal vector, and we're pointing in.
there you get a negative one.
Yeah, so what's the interpretation of this? Well, it's passing through, right? It's leaving the space that I'm considering.
you just have some direction.
You guys see that? Like I said, we're gonna have to work on this normal vector a little bit.
Yeah.
Because, right, a surface, kind of in general, of course, if I look at a point, there's a perpendicular vector this way, but there's also one this way.
Yeah.
Right, and so there's an orientation consideration. You guys see that? So when we do surfaces, we'll have to tell you which way they're oriented. Cool? But really that amounts to just a choice of n or minus m. Cool?